Good afternoon, everyone, and welcome back to the Adobe Connect version of this series of webinars. This one, as I believe Mike may have said, is being recorded and will go up on the Astrobiology website shortly. Other things to be aware of is that we have two presenters today, Matt and Francis, who are going to go through waving there, going to go through the overview of their paper. After this presentation has finished, we will change the status of the paper, which you can get to straight from the front of the Astrobiology website, so that it will be open for comments. And just in case anyone hasn't done this before, what that means is you can't edit the paper directly, but you can highlight any piece of text and do the equivalent of add a post-it note to it. We have, over the last few weeks, also been setting up discussion threads for each paper, but so far no one has actually used those. So unless anyone wants to send an email to support@noinnovation.com, we won't set up a discussion thread for this. It seems to be working much better for people to write directly into the papers, and then if the conversation becomes too complicated or you want to talk about things at a higher level, then we can set up a discussion thread. So we have the presentation. You are welcome to ask questions as we go along. I can see Brittany is just typing here right now. And actually, Brittany, if you have a camera, or actually, even if you don't, would you like to join the presentation panel? Because Brittany is obviously one of the authors of this. And while she is thinking deeply about that, if you do, we will bump you up to be a presenter. But in the meantime, Matt, let me pass it over to you.
All right. Well, let me go ahead and hi, Brittany. Begin with the sort of the overview of this. This is, I guess, one that we are discussing as far as origins of life, emergence of life with respect to the environment, and there's an intercoupling of these two. And by all means, if my if any of the other authors in this have comments or that, please let me know or what have you, and add it in as you need to for some of these areas. Being a group effort, it certainly has some ideas that I may not pass along, as well as some of the other authors. And by all means, please feel free to chime in as needed. And so as sort of a getting started part of this, sort of the explanation for why this PowerPoint or this presentation was even designed is that there is an interplay between life and its habitat. And that is certainly true nowadays, that many of the metabolic processes and that are intimately tied to the environment and the various chemistry and physical processes that are available within that environment and have in turn infected them as well. So it's sort of a very much a interplay between these two. And so presumably life and environment are intimately related. And for the emergence, the habitat or the environment probably was very important in determining life. And the early evolution, the ability to diversify in those was an important part of that as well. And so some of the other points that may come up with this as well are that the requirements of life on a very broad scale may be universal. If we are looking for life on certain ways, we are looking for very fundamental parts of life. So things that perhaps organic carbon or things like that, if we wanted to stay within the realm of organic organisms, or energy gradients, or perhaps even proton or electron gradients as well. And by many ways, an interdisciplinary approach will be required to assess these environments, both from a chemical, from a geological, from a biological, from an astronomical, and many other perspectives. And so this is definitely one that requires a multitude of different fields to sort of address certain the aspect of environment and emergence of life. I think I've gotten that all covered there. So sort of the major goals of this that we highlighted within the paper is understanding the conditions for the origin of life on the Earth. Those are the environmental conditions. There's a number of other conditions that play within that as well, chemical and sort of physical, but sort of a geological or a type of conditions are important for those. And by understanding the conditions for the origin of life on the Earth, there's certainly a very clear application to other planetary bodies and the search for life elsewhere. At least if we're hunting for Earth-like life, finding out how the conditions are for the Earth would certainly be very useful for understanding other Earth-like life on other planets. And so part of this requirement is to identify key factors within the origin of life. So what are some of the ways of trying to approach this, whether or not carbon or various other elements, phosphorus, nitrogen, sulfur, are key factors in the origin of life remains certainly an open question, which can be approached at from both in sample analysis on a variety of different environments. You have only a limited geologic record, but there's still information to be extracted from that, as well as laboratory experiments, which might deduce methods of production of certain types of compounds or liberation of certain elements from the environment, or other thermodynamic properties or kinetic properties that might start kicking in and encouraging various environmental features to start coming about. And so related to this is finding the environments in which life could emerge versus where it could have persisted. This brings to mind the complementary yet competing ideas of fertility and fecundity. And so fertility in this way is where life might have arose in sort of a certain, very much a key environment might have been more conducive to originating life, but where it might have diversified and thrived would be a more fecund environment, where it would certainly be, those may have persisted for a much longer time, geologic time, than the fertile environment. And so both of those are within that area of active potential research within this subdocument of the astrobiology roadmap to come. And so we divided this up into sort of four major categories of questions, from the geochemical considerations for the origin of life, as well as planetary. And so the stretching of those two together is an important process here, as well as understanding how organisms and environment relate to each other as far as affecting each other, and identifying ways that those two might be able to be correlated, and especially with respect to biological emergence. And then finally, the environmental precursors, what sort of environmental processes were sort of encouraged the emergence of life in the environment, would definitely be an important major sub-question within this broader question of how do the Earth and environment related to each other as far as origins and early diversification. So within the geochemical questions section, we have we highlighted, I think, 10 different questions, and so there's in total, I think, about 20 questions, 10 of which are within the geochemical, and that's due to our own bias as partially geochemists, and for certain, if there's other questions that are coming out from other fields within the astronomical or planetary realms, please feel free to add them within comments. And so the geochemical questions include a number of different things, including what was the role of mineral surfaces acting as enzymes or sort of catalysts in early biogeochemistry, and did it play an important factor in the origin of life. Another example of this would be the certain types of clays that may catalyze RNA synthesis, or sulfides that may promote reactions that are sort of reduction of carbon and perhaps other catalysis within life. And so the mineral part of life is an important part of the environment, determining emergence for certain. And then the next question would be, what are the necessary bioavailable minerals or elemental components for early life? A big question for my own research would be phosphorus availability for biological systems, whether or not there are other things that might be able to substitute. For instance, glyoxylate or arsenic would be substitutes for those sorts of materials, and certainly are available open questions for other materials, sulfur and selenium, looking at my periodic table, as well as a number of other materials too. And so the next one, what novel inorganic mineral structures aided the formation of complex organic molecules? This includes a number of various types of clays and certain other materials that might have been helpful in sort of promoting organic biochemistry, and perhaps there's an interplay between these two. And another, I guess, area that this might cover would be sort of rock membranes or vesicles within rocks, and the interplay between determining how similar those might be to cellular processes. And it's certainly an open question, sort of a mineral mimicking what we have in modern biology question, and there's plenty of room to sort of expand on that idea as well. Then within the next question, how do we go from simple organic compounds to increasingly complex compounds? This is a broad question that is asked throughout these last few documents as well, and will continue to be asked within the next few from the origin of monomers and then the origin of polymers. This one is sort of within that branch of the influence of the environment within those two as well. Continuing with the geochemical questions, again, we have most of our questions within the geochemical realm. The physical and chemical thermal gradients, what extent were those necessary for the within the inorganic and the organic precursors are required for the emergence of life? For instance, proton gradients, redox gradients, thermal gradients, so temperature differences. How critical were those for sort of varying chemistry and promoting sort of disequilibrium chemistry? What environments are there for those sorts of things, both occurring geologically and on a planetary scale, and how might those have influenced the biological processes? Next one is a fairly distinct question that, of course, we do not know the answer to, but it is the presence of an atmosphere required for the emergence of life. And we have at least had on this Earth for a long time a very clear and thick atmosphere, but whether or not atmospheres are necessary, and the broader question, how volatiles could have incorporated on an atmosphere-less body, such as the moon or on an asteroid, and are those is the atmosphere an intrinsic part of life or development, emergence of life, or is it just a beneficial aspect? And so this is an open question. It may not be obvious how to answer that question, but there are certain ideas that might come in with that for certain within this field of sub-questions here. Then next one, what geologic environments on early worlds would have produced organics and liquid water? This is certainly and has a very broad overlap with other questions, including polymers and monomers. How were those generated on early Earth and within the planetary scale as well? Presumably there are certain requirements for those, and what were those requirements? And then related to that, did indigenous or exogenous organics and volatiles, such as water, play a larger role? Which of those two might have played a larger role in the origin of life? Given that these things can be both produced through indigenous and exogenous processes, which of those two might be more relevant in this case? I think there's two more geochemical questions. Yeah, what solvents influence the origin of life? Within the document, we specifically highlight water as being the most important one, obviously, but also lipids acting as a cell membrane create a hydrophobic layer that causes certain chemistry to occur, but you can also envision that other types of solvents have been invoked in both in origin life studies, including formamide and ammonia and a few of these others, and so those might also certainly be relevant in the origin of life and the development of it on Earth and on other planetary bodies. Then the last one, what physical, chemical, and thermal gradients were required for the coexistence of organics and liquid water in various geologic environments. And so these environments were certainly fairly important in sort of developing geologic environments that might be create certain chemical disequilibrium materials and encourage sort of a large-scale mixing to do some of these, so to do some of the prebiotic chemistry and origins, early life might have depended on these sorts of large gradients. And so what scale must those have been on, and if they're micro or macro scale, it's not certain at all. And so those are the major geochemical questions we identified. There's a number of others that might pop up as well, and certainly we do encourage others to help us find and address some of these questions and expand on these as well. Let's see, having gone through geochemical, Francis, Brittany, any comments you'd like to have on those?
I think you covered it pretty well.
Okay. All right, well. Okay. I can move on to the planetary.
Just 1 second. Francis, can you put your phone back on mute, please, because we're getting feedback. Great. Cheers.
Okay. All right, so the next set of questions comes about from the planetary scale. And so, of course, if we are able to establish the geochemical scale for life in certain views of that, we can thereby sort of expand that to the planetary scale of things as well. Okay, and I see Ron has pointed out liquid methane and ethane could serve as aqueous solvents for extreme cryospheres like on Titan, and that is certainly a very true point here as well, and it would be certainly would fit well within the alternative solvents ideas that might pop up and could be quite valuable with understanding some of the chemistry that is going on with those, especially since you start changing temperature and pressure and various other scales as well. All right, so the planetary, that does bring us fairly well into the planetary scale of things. So alternative solvents may certainly be a lot more important as you move around in your pressure temperature regime and compositional regime within the planetary environment, moving into sort of organohydrocarbons. And is there? Okay, so what those might actually be important on these in different planetary environments. So let's go ahead into the planetary. And so, John, you say, what is a timescale over which an environment must persist to be conducive to the emergence of life? Yes, not so much is there, because obviously there is, it's just what is. And so what is the timescale over which an environment must persist to be conducive to the emergence of life? And you can consider this within at least the terrestrial context, where the potential for impact frustration of life might have caused various environmental catastrophes and burned off whatever little happy little warm little ponds might have arisen, might have gotten vaporized by a couple choice meteorite impacts. And so especially if the late heavy bombardment happened to have pelted the early Earth. And then how many times did life emerge on Earth before it persisted? This is not exactly a question that might be easy to identify, but might be one of those that it would be a geologic question within this environment too. And so, for instance, if we have some constraints on how much damage happened to the early Earth and other environments, or sort of if various other processes on other planets might have been present too. And so Brittany is typing now. Also, things like how long would a subsurface ocean on an asteroid or moon need to remain or stay active before it's dead? Okay, so for instance, on another planet, Ganymede or something like that, how long the liquid water ocean might actually persist at least on the surface, or I can also think of an example on Titan. If you have an impact basin that forms a water lake out of the icy crust, the length of that might actually be a length of duration of that material might be very important for sort of mixing some of this material. And if life can arise quickly, how can does it have the staying power to diversify and move into other environments? So, or before it is alive. So the next one is, did life originate in a single environment or from mixtures of multiple environments? This is an important one, especially from the perspective of geochemistry. We can envision certain environments being conducive to certain chemical systems arising. For instance, a reducing environment may be important for forming certain organics, and if you're able to mix those two with mix it with another environment that might have different environmental systems, might be an important process. Understanding how you might get those two disparate types of chemistry, mixtures of multiple environments, and then mix the two of them would be certainly an interesting question here. How long can stable disequilibria, how long can they be sustained, and in turn, how long can life be sustained in a static world? Is certainly an open question for these other two that Brittany raises here as well. And I see also relevant to Enceladus, yes, subsurface ice oceans now thought to be ephemeral and located at the South Pole. Okay, so in that case, the liquid water that we presume might be necessary for life may not persist for any length of time. Titan's atmosphere is a similar case too, that the organic material that we see in that is raining out has a lifespan of about 10 million years and should not be there right now, but it is, and so that implies certain chemistry might be coming along with those things as well. What planetary conditions lead to energetic prebiotic environments? And so how do we get the energy part of life out of these materials, and is the energy enough to sort of promote different chemistries? And so changes in things like stellar irradiance, geologic cycles, plate tectonics, radiogenic decay, water rock cycling, those sorts of things set up different environments and allow for different energetic systems, and would certainly be useful in understanding planetary scale environment organism interactions. Let's see. Francis, Brittany, anything else? Have I left anything out? Thumbs up or all good? Okay. And then the next sub-question within this talk is how organisms and environments are related to each other. And so, for instance, what was the role of compartmentalization and exchange in the origin of life? And we highlighted the word exchange because compartmentalization alone is not does not make for life, but exchange with the environment is a necessary part of compartmentalization in order to keep things out of equilibrium. And identifying those processes is a very important, identifying those environments is a very important part of understanding much of this material as well. And so compartmentalization has several relevant scales for biology, including things like our cellular to organismal. And on the same scale, the compartmentalization is common to, for instance, water environments, from small bodies of water to oceans, and in mineral structures as well. And so how these environments are capable of compartmentalizing the scale of those and how they can actually exchange with the surroundings is an important part of how environments interacted with organisms as well. Were biological adaptations for the survival of early life forced by or derived from the physical environment? This is, for instance, was early life messy? Is the text within the document here. So messy life presumably means one that is able to tolerate a diversity of different organic substrates, minerals, things along those lines. Presumably, a messy life would have had much greater fecundity and been able to spread around and diversify a lot more easily than one that is stuck on a specific in biochemical pathways. And in modern life, at least, as far as definitely one that is very much diverse. However, how diverse early life might have been would have been an important part, and so how quickly could it have diversified out from there, including things like changes in pH, water availability, redox, and a number of other things might have been quite important for sort of understanding how quickly environments have to adapt, and thereby how quickly organisms would have had to adapt as well. And then the final one here is what environmental conditions provided energy for prebiotic processes. And so the production of energy is fundamental to all life. And so production and utilization of environmental energy is certainly useful for all these things as well, given what are some of the ways that environments could have supplied energy for life. And there's a lot of different ways that life does it as well. And so, John, you have a question here about prebiotic as meaning the conditions that do or should lead to the origin of life. Certainly there's prebiotic. For instance, the moon would be prebiotic. Yes, that is true. And so that's a good point, that prebiotic we are using here is before life, yet followed by life. And thank you for making sure that that point is clear, or is clarified here. And that will be one that we will try to change within this document as well. Let's see, what environmental conditions provided energy for before life, but followed by life processes? Yes, okay. And then the final set of questions that were highlighted by this group right here is that, is there environmental precursor or analog for information transfer? And so information transfer for certain consists on the small scale on a chemical recognition. And so crystalline substances have a sort of very low level information transfer, yet how high a level could there have been from sort of environmental process and sort of a inorganic organic mixture or something along those lines. And so information transfer in early life might provide some information on this process, and we might discover how much functionality might have come out from that system as well. And so what physical, chemical, and thermal gradients were requirements for the origin of life? So the gradient idea is still an important one that you've seen throughout this the document that we've discussed so far. So these gradients set up the disequilibrium system necessary for some of the chemistry that comes about from here. And so sort of continuing what those things were is sort of a little bit of overlap with some of the previous questions as well. And then, are there structural or functional analogs for cells, membranes, and other biological elements within environments? And so, for instance, sulfide bubbles or some material like that might serve as membrane analogs, or other material as well. I saw a question from Ron, but it appears that has gone away. So, or a comment from Ron, but okay. And then the final one that we identify here is how much diversity in geologic environments is required to produce all of the prebiotic chemistry. And I guess that definitely that word "all" will be highlighted. How is produced sufficient prebiotic chemistry required for the emergence of life? And so I guess if you tie a prebiotic into before life but followed by life, that would be a little bit more reasonable view of all. The word "all" there. And so required for the emergence of life. Presumably life, of course, we'd have to get down to the very fundamentals of where life is, and is this question even addressable is certainly an open question within chemistry and elsewhere as well. So that is our basic overview of the questions that we've highlighted. Each of these questions, if you take a look at the document, is expanded upon in greater depth and with better examples than I probably have given in this half hour. But please do take a look and feel free to comment as it comes along. And I see that, Ron, given all the prerequisite materials and physical conditions for prebiotic places to become biotic, the $64 question is how long should emergence take? And that is an excellent question. You highlight 500 million years. That would be a fairly long time from many of our perspectives as chemists, but can it be a much shorter time is possible? For instance, Mars was a lot more nice place to live back in the 4.5 to 3.5 billion years or before present, and so maybe that environment might have been better for that process as well. That is the end of this document here, the presentation. So I will leave Francis and Brittany, if you have other comments or if I missed something, please feel free to pipe in.
There is the rustling of paper, which suggests thinking.
All right.
No, Francis, Brittany, nothing at the moment. Let me, in that case, well, in fact, as Mike has just said, phone lines are open. For anyone who may want to ask a question directly, if you have a look at the top of the screen, I always get this the wrong way, sort of over here, you'll see someone with their hand sticking in the air. Oh, Brittany, I can see you've opened your mic. Did you want to say something?
No, I just wanted to say I thought that was a pretty good summary. We were just trying to think about how biologic systems and planetary...
Hey, Brittany, I think it's kind of hard to hear you. Remember, we're doing the audio through the phone, not Connect.
Okay.
So just respond through the phone line.
Can you guys hear me?
Much better.
Okay. Yeah, so I just wanted to say that I thought that was a pretty good summary of the discussions we've been having. It was basically how to think about planetary systems and biological systems in the same light and how they might work together, how they might be similar and different. So that's kind of the theme for the whole document. And I thought just on the planetary side, it was thinking about what parts of a planetary system are really needed. So to kind of answer that static question, we talk a lot about in planetary science, this environment has water, this environment has ice, this environment has whatever, and then the big question is that really a habitable environment, or does it require activity? Does it require other ingredients or other systems to be active in order for that to be really astrobiologically relevant? So that's kind of the planetary side of it.
Great.
And,
oh, hang on. Someone else has got their mic open.
Yeah, it's me. Can you hear me?
Sorry. Yes.
Yeah.
Go on, Professor.
Just to expand upon that a little, a lot of focus typically gets put on the presence of water and the activity of water. But for all the other ingredients needed, they're not always necessarily in the same stability field as liquid water. And so we wanted to expand upon the, parameter space that we're kind of observing. So consider things like oxygen pheacity, the stability of organics, and where the stability of organics overlaps with the stability of liquid water, and how that's going to change from body to body or even different environments on the early Earth. And those are the kind of steps forward that we need to start making, because now that we've discovered water on Mars about 27 times, it's time to start thinking of other ways to put this information into context to better understand and actually identify habitable environments.
Great, thanks. Okay, so what we're looking for now is, as you've seen, you're welcome to type questions into the chat box, but if any of you want to actually ask your questions directly or make statements and observations, you're welcome to do it. What seems to work quite well is if you use the little hand icon, and I'm just going to turn mine on there. So if you look next to Andy Burnett. All right. And with that, a sudden blast of interest. Okay. Well, let me take the first one. Brunner, if you'd like to ask a question.
Can you hear me?
Yes,
can you hear me?
Yeah.
I want to bring to the attention of the group the wonderful paper that was given by Steve Benner in Florence, Italy in August concerning the fact that if current theories are true, that the Earth was completely covered by ocean and therefore could not have developed certain key minerals such as molybdates and borates that are needed to bring into existence the R of RNA. That's assuming, of course, that the RNA world is the current darling theory of the origin of life people. But if nothing else, I think his paper should be put on the resources of this website for people to look at.
Yeah, do you have a link to the paper? I was going to say, by all means, pop it into the chat window.
Right. I don't, but I can send the paper as a PDF if you tell me where to send it.
Let me just, if you send it to that address, that would be great. And then we can, and also actually anyone is free to upload documents onto the Astrobiology website, but by all means send it and we will do that. Okay.
All right, well I'll be sending it later.
Lovely.
Here, but I'd like to get comments about that.
Yeah, I can make a related comment. There was a new paper in Nature a couple of weeks ago about an alternative interpretation. So the assumption that we have an early Earth, all ocean scenario, I think, is probably related to the Hadean zircon data, which seem to imply the same temperatures as exist at subduction zones. Currently, those having possibly occurred in the same, basically, water stability as in the Hadean Earth, and so that's one of the data points that they point to. There's a new paper out in Nature about heat pipe volcanism and how that might have the same effect. You might engender the same geochemical situation at a different initiation point for plate tectonics. So that's another theory. It's certainly not. I would say that whether you have an ocean world or a runaway volcanism at the same point in time, you can get similar temperatures out of the same situation. Or out of both situations. So that's another theory that's out there. So I'm certainly aware of so, Steve's point is interesting. The Hadean data that has been pointing to this is from one reservoir. So it's quite possibly not a global or either a global average or a localized data point, but there's also many other interpretations for that data set. So I think those are the types of questions we don't want to pick up on one thing being the answer or the other thing. It's to write the right question that people can take this as a field of study, and then we can actually have these conversations about what each of these data sets imply. So I think that's really pointing to not a result but a question, which is what really was the early Earth like, and that's the same thing. What were the timescales? What were the ingredients? What were the environmental precursors? So both of those situations might point to the same thing. So I think that's hopefully been stated in a generic enough way that it opens up fields of research that talk to each other in such a way as has just been suggested.
Interesting. Okay. And any other comments to that? Otherwise, we'll go to John.
I see Ron has a comment here. Plenty of boron as well as molybdenum and tungsten in soda lakes in volcanic areas. And his idea, at least if I remember reviewing it, was that it was that these sorts of materials are less common in sort of until plate tectonics has had to set a chance to kind of kick into gear. just to elucidate, to illuminate, I guess, what a bit of Steve was mentioning back in the time. But I certainly agree with Brittany that it's a question to be asked within the whole, and is not is certainly I know the abstract at least was a suggestion to the community for putting out an idea, and it would definitely fall within this realm of area that we have talked about here today too.
Absolutely. So let me just take that moment to encourage everyone. As soon as we're finished here, we'll open it up for commenting, and do insert your thoughts on the paper to make sure we don't lose anything. John, you've been waiting patiently with your hand up. What would you like to ask?
Yeah, it's not hard to raise your hand here, so that's not bad. I was along the lines of Ron's question, though. I would think that a soda lake and a completely covered globe would be inconsistent, but incompleteness in the coverage of the globe with an ocean is probable. Meanwhile, I did want to point out that the origin of life always sounds like a demarcation where you go eureka, and then there's some hungry organism looking for a place to eat. And I think that the origin of life is unlikely to be a single event, but is a continuum over time, the coexistence between an inorganic and organic world, all in the same place. And not only do you have to get the first organism out there, who presumably will continue to be nourished by Mother Earth, but you've got to get a second organism, and a third, and a fourth out there. So looking at the origin of life as how a community develops, I think would be a wise thing to do, rather than to look for that kind of eureka moment.
I see heads nodding. Anyone want to chip in on that?
I certainly think that's reasonable, and for certain that there's terms that are accepted, and I guess that, or not terms that, there are terms that are well used, and that is one of those. The origin of life. There's a whole journal dedicated to it. Although it's community-based, it would be inconceivable to have one cell come out from this process rather than sort of a community for certain. And so I agree with that.
That's why they have evolution of the biosphere as the second part.
Right. Yeah.
Okay. Sorry. Go on, Francis.
This also gets into the kind of distinction between habitability and the emergence of life. You know, if you have the emergence of life, then can you have that in a non-habitable environment, or do you need to develop a habitable environment in order to have the emergence of life? But it seems like more of a philosophical question.
Chicken and egg quality there. Any other questions there? Anyone else want to pop their hand up or type into the document? Type into the chat window, sorry. No? Okay. Thank you very much. If you give us a few minutes, we will change the status of the document. Thank you to our presenters. And thank you to NASA Ames for bringing up the Adobe Connect system again. I'm sorry, who was that?
Another. One bug's poop becomes another's breakfast, creating
Comments are still being typed.
There we go. Oh, okay. Thank you. Yeah, you're right. Okay. Thank you very much. Let's wrap this up at that point. We will go and change the status of the document. Thank you to the presenters. Thank you very much. And our next session is tomorrow at the same time. Thank you. Cheerio now.